these two metabolic pathways are going to be coupled with respect to each other. And so many times I just call it the ETC or OxPhos. And there are 4 multi-protein subunit complexes that do the electron transport chain. However, the electrons never go in order from complex 1, 2, 3, and 4. If you start off with NADH, then it's going to go through complexes 1, then 3, then 4. If the starting material was, this is frozen up already, if the starting material is FADH2, then it starts off with complex 2, 3, and 4, but you bypass complex 1. Okay, so it's either 1, 3, 4 or 2, 3, 4. And that's going to be one of the reasons why there's a difference between how much ATP you get per mole of either FADH2 or NADH. And that'll make more sense once we go into more details with respect to each of the complexes. Okay, and the mitochondrial matrix, is it going to have a high pH or a low pH relative to the intermembrane space? It has the high pH because this intermembrane space is where they're pumping all the protons to. So since you have a high concentration of protons, that means you're going to have a low pH since it's an inverse effect. Okay. And the one that looks like the inverted mushroom is the ATP synthase, which we'll talk about in greater detail. That's where the oxidative phosphorylation actually comes into play at. Yes. So we went over the 4 complexes. And so many times they're just called complex 1, 2, 3, and 4. They also have other names, very, very descriptive names, where we had complex 1, which is NADH ubiquinone, which ubiquinone is coenzyme Q. Ubiquinone oxidoreductase. And so it's going to do the redox reaction between NADH and coenzyme Q. We had complex 2, which is succinate CoQ reductase. And it's the one that's linked to the citric acid cycle. And it's where the electrons from FADH2 eventually get passed off to coenzyme Q. Then we have the cytochrome BC1 reductase. It's also called complex 3. It's also called the BC1 complex. Okay? And that's one that I worked on in one of my postdocs. And so we'll go into greater details with that. And that's where the coenzyme Q goes through what's called the Q cycle. And the electrons ultimately get shuttled to cytochrome C. You don't want to confuse cytochrome C1 and cytochrome C. I don't know why they named everything the way that they did, because it can be a little confusing, but cytochrome C is the only protein of this chain that is not in the membrane. Okay, it is actually peripheral protein. If you think about what was a peripheral protein, what does that mean from last semester? Right, it means it's not anchored into it or inserted in, but it associates with the external portion, the outside portion of the membrane. Okay, and so what it does is it jumps from complex 3 to complex 4, and then cytochrome C oxidizes it. So then the electrons go from cytochrome C to ultimately to oxygen to form water. Okay. We're going to go into detail with each one of these later on. And I did check, and I don't know how, the song is still up. It is definitely a geeky song, but anything to help. Oh, let's see if we can get it to work. Oh, now it's going to go like 3 different times. Of course. That looks like who? Oh. I didn't say he was a good musician. And that's complex 3. And thank you for that one. Okay, so there are plenty of videos out there, and many of our previous students have made videos concerning the electron transport chain. All right, so, complex 4. This is ubiquinone, which is coenzyme Q. And so there are 3, unlike like FAD, FADH2, there are 3 distinct forms of it. And so we have the ubiquinone, what's called the semiquinone, which is where it's actually a radical, where 1 electron has been transported to it. And then we have ubiquinol, which is also abbreviated as QH2, where now both electrons are on it. So is the ubiquinone, is that the fully oxidized or the fully reduced form of coenzyme Q? It's fully oxidized, whereas ubiquinol is the fully reduced form. And so if you notice, there's a huge hydrophobic anchor right there. And so coenzyme Q it never leaves the inner membrane, presumably if you're healthy. So it stays inside the membrane. Okay, so you don't have to worry about it by the semiquinone getting loose and going out there and attacking things. In fact, you're going to see that it's important the semiquinone is the radical because of the way its role in complex 3 and quite possibly complex 1 as well, because you can transfer the electrons one at a time. It's not like an all or none, okay, which is important because it keeps the cycle from being short-circuited. Okay, so if it just says Q, that means it's oxidized. If it says QH2, that means it's fully reduced. Okay, and so many of these proteins have what's called iron-sulfur centers. Of course, iron is a trace element metal that you need to have. It's involved in redox reactions. But what is the sulfur? What part of the protein can be the sulfur to hold the iron in place? What part of the proteins are going to have sulfurs? Okay, and those come from what amino acid? Cysteine. And so these are very important cysteines. And so there are different geometries that they can have. They can be like square planar, they can be octahedral kind of based, tetrahedral, so on and so forth. But the geometry of it actually affects the electron potential. But yeah, there are important cysteines that hold these irons in place. And you're going to see, a lot of times they're just written as FES, but in reality, those are iron-sulfur centers that are parts of the proteins that will just help shuttle the electrons on through the chain. I actually don't care for this cartoon right here because it makes it look like, I don't know, I just don't really care for it, but it's easy in the sense that it clearly depicts, how the electron transport chain ships the protons from the mitochondrial matrix to the intermembrane space, and then ultimately it was going to push it through the ATP synthase. Okay, but like for example, cytochrome C is not even on there, even though it's really important. But I do like the little figure here. But now the energy releasing oxidations give rise to this proton pumping. And so I'm not so much worried about you knowing, oh, which complex does 2 molar equivalents versus 4 molar equivalents. Because, for example, with complex 3, are we talking about 1 full Q cycle? Or is it, so I just want you to know which complex put protons across the membrane, and I don't care so much about the molar equivalents for it. Okay, so it's complexes 1, 3, and 4, which ultimately put the protons across the membrane. And complex 2 does not. Okay, but this causes that difference in the concentration gradient. So there are more protons in the IMS than in the matrix. And so because of this, it's going to cause this allow for the diffusion of the protons back through the ATP synthase in order to force ATP to be made. And it really does look like a turnstile. Okay, so this is the way that many times they depict ATP synthase. They have what are called alpha and beta subunits, but those are not alpha helices and beta sheets. That's just the way that they designate it, unfortunately. And it's got this stalk region. The part that is where this is the part that is where the ATP is made, especially in between the alpha beta subunits. And this is the turnstile portion where the protons come through, and it causes this acts just like a ratchet, causes it to move. And we've got actually some figures that do a really great job of showing this. Okay. So the one part one thing I want to point out is that this portion here, the way it's drawn, this is the mitochondrial matrix. This is the intermembrane space. Some people, get confused by that. The side that has more protons on it is going to be the intermembrane space. Okay, and so that's why the protons flow through the turnstile and cause this to turn. And so they've been able to crystallize this in various parts of it, I should say. And based off of that, there's a video that they put together that shows how the ADP and inorganic phosphate are literally forced to come together to make ATP. Because remember, it's not energetically favorable at all. In fact, it requires, about 31 kilojoules per mole under standard conditions. Okay. Let's see if I can get this one to... This is really cool. At least I think it is. There's no sound, though. So we can see there are 3 spots. Some places call it the open spot or empty spot. The A spot and the P spot is the way that I learned it. And so that's why I'll refer to it as. And I'll draw a little picture of what I mean. So the middle is like the turnstile. Now we're going to see literally how these alpha helices cause the different subunits to switch their conformations. And so what happens is that at any one time you have the ADP and inorganic phosphate coming in, whenever a proton goes through, it's going to force them together to make ATP, and then you always have one spot that is open or empty. And so let me draw a little cartoon showing that. And I put this video also on the webpage, and so that way you can look at it on your own after you have had time to mull it over. So, so the way that, this is a very, very simplistic drawing. Between each of the alpha-beta subunits interface with another alpha-beta subunit is where you have the binding at. And one site is the site that I learned to call it A, and then the P and the E, or you can say O for open, E for empty. And the P is where phosphorylation occurs, and the A is where you already have the reactants coming in. And so what that means is that at any one point in time, as the protons move through, it causes a shift. And so what had been the A site, and I'm going to try to erase it so that way you can see what I'm talking about here. The E is still empty because it's open. There's nothing in there. But on one side, oh, whoops, I forgot to have it on erase. On one side, we have ADP and the inorganic phosphate just coming in. Okay, so it's there. And the other side already has the product, the ATP product from the previous reaction. And the one side is empty. What happens is as the protons pass through and it causes that turnstile to move once, we actually get a shift. And so it causes the phosphorylation to occur on the one that's in the upper left-hand quadrant. So since it caused it, it forced it to become ATP. The ATP that was made the time before gets released, and so now that's the empty site. And what happened in the empty site is where the next ADP and inorganic phosphate come in to bind. Okay? Then we have the next round of protons that come through. And whoops. Sorry about that. They come through.
And the protons are what makes it turn.
And the protons literally it's just like a little turnstile that you were trying to go through at the subway or at an amusement park or what have you. It causes the protons go through the turnstile. It causes the conformational changes to occur between the subunits. And so I'm going to have to draw it down here just because of the fact that I'm kind of running out of room. So what had been the mature ATP from the time before, it's now the empty site because the ATP has left. What had been the empty site now binds ADP plus the PI. And then what before had the ADP and PI, it's forced together, like literally crushed together to form ATP. And then you have more protons go through, and then we're back to where we had at the beginning, where what had been the empty site now has the ADP plus inorganic phosphate. What had the two reactants now has the product ATP, and then what had the previous product ATP is now empty, ready for the next round. And so that's why it's constantly going. Because if you think about it, ATPs are energy currency that we have to use. And we use, for like every muscle contraction, if you remember the little beads, like they like to show the way it looks like with little ratchet beads for each muscle contraction, each time that moves, you have to use up an ATP. And so just think, every lifting your finger, you have to use up scads and scads of ATP. So you have to constantly be making this. And it's our mitochondria that does that. Okay. All right. And just because, well, these poor, I think they're Japanese students, but they still depicted it in their own unique way. Let's see, it's the title. I won't make this one large, but it's only a few seconds. There we go. So we have the one that's like the middle one's the alpha helical turnstile part, and then the three alpha beta subunits.
They stole my idea.
Yeah. Faith integration.
Interpretive dance.
Interpretive dance. There's nothing new under the sun.
Can we do this for extra credit, perhaps?
You can't do the exact same one unless you want to one-up them, but yes.
Play
Get it on beat.
But there we have it. Okay, so this is called chemiosmotic coupling, which is just a fancy term for what we've been describing so far. And so this is just putting in words what we have, and it's very text-laden, which I don't like. But there's that proton gradient because of the fact that there's an asymmetry. It's asymmetrical for these proteins that are in the membrane. And one other thing that I want to point out is that many times in some of these, they're going to, instead of calling it the matrix side and the intramembrane space, they call it N and P. Okay, and so you may even hear, and maybe in that one song, you may even talk about the N or the P site or something like that. And let me just show you real quick what that means. And so if we go back to our, little, this is not drawn to scale. That's going to be the outer membrane and the inner membrane of our mitochondria. Since there are protons constantly going from the matrix to the inner membrane space, so I'm just going to draw one, but there are many, it causes a charge differential. Okay, if you're healthy, that is, it's going to cause a charge differential. And so because of that, we now have more protons on one side, and so you've got all these pluses. So that's called the P side of the inner membrane, and you have a lack of the protons, or less protons, on the matrix side, and so it's more negative, and so that's the N side. The inside is really the inside. Ha 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 ha. Okay, but hopefully I can help you remember if you forget, just in case that either I say, oh, this is on the N face of a protein that's the part of the protein, that complex that's on the matrix side, whereas if it's the P face, it's going to be the part of the protein that's on the inner membrane space side. There we go. And the reactions of NADH, CoQ, O2, and even FADH2, which I don't know why I did put that on there, they all require protons. Okay, so now the one thing of it, I know the reason why I didn't put FADH2 on there is because the protein complex that it's in doesn't transport them all the way across the membrane. So that's the reason why. Those protons stay in the matrix side, the inside.
That's complex 2.
That's complex 2. Okay, and whenever we look at the crystal structures, it's pretty it'll be obvious the reason why that happens. All right, so this is showing what happens if you start with NADH. So we can see there's a general flow of electrons. I mean, we're showing it left to right. By the way, sometimes they call this the respirosome. I've got a picture of it in a moment, because they're really not spaced out this far, obviously. You have to realize we have to, complex 3, the one I worked on, if you're healthy, the risky protein in it has to be able to move at least 100 to 200,000 times per second, okay? Or otherwise, you're sick or you die. And so that means every time, and that your cells have more than one mitochondrion in it, and each mitochondrion has more than one respirosome, and some of your cells are going to have gazillions, lots and lots of mitochondria, so you can imagine that they're just constantly pumping out these electrons. And so they're highly, efficient, but there are mistakes do occur, and especially that's one of the reasons why it believes for aging, and even for some types of cancer that we've talked about in some of our other classes, where the mitochondria start to fail. And so there are fail-safes put in, and then whenever they start to fail, then you have to make sure that that cell is taken care of. Okay, so we have this general flow of electrons, and they're showing it from left to right. And I would expect you to be able to draw a cartoon version of the ETC. I wouldn't be surprised if that doesn't show up on a quiz or an exam. And so we have complex 1 utilizes NADH. And so that's where, if you started off with NADH, where would this NADH come from? Which one of the possibilities? Citric acid cycle. Okay, so we have a citric acid cycle because it takes place in the mitochondria matrix. That NADH does not come directly from glycolysis, because where does glycolysis occur? Cytosol. And so we're going to find out NADH cannot cross into the Holy of Holies. And so we have to find there are ways to get around that. Because you want the electrons to get into the inside of the mitochondria, but the NADH cannot cross over. All right. Oops, sorry. I went too far. And so just in general, what happens here is the electrons ultimately, and I'll explain this in greater detail whenever we look at the crystal structures, but the electrons ultimately go to a waiting coenzyme Q. So CoQ, which becomes QH2. Then it's going to move through the membrane to complex 3, the BC1 complex, which happens, that's where the Q cycle occurs, and I'll explain in greater detail how that happens, because that's probably, at least, even though I worked on it, I always thought that was the most difficult part to explain, to understand. And the figure in your book, I even found that confusing, and so I had to sit down and think about it. Okay, and then the whole purpose of complex 3 is it's going to be pumping protons across, but it takes the electrons from coenzyme Q to cytochrome C. And if you notice, cytochrome C is the only one that's not stuck in the membrane. It's a little protein. It's not a separate complex. It's a relatively small protein compared to everything else, and it just jumps or moves in the intermembrane space from complex 3 to complex 4, passes its electrons through copper, actually. It's the only one that uses copper. And more protons get pumped through because oxygen gets reduced all the way down to water. Okay. And so that's why complexes 1, 3, and 4, they push protons from the inside to the intermembrane space. But if we had complex 2 on here, it would be somewhere down here, and it utilizes coenzyme Q, but it does not put protons through. So, this is what has been crystallized so far. If you think back to last semester when we did protein structure, remember it's actually quite difficult to crystallize hydrophobic proteins because they're not going to be happy in aqueous medium. And so many times you can do only the soluble part, or primarily the soluble portion. And so to me, this, you can either think of this complex, and there are multiple proteins in it, as being like a gun, or the letter F, or if you flip to the other direction, it kind of looks like the state of Florida. So, but what happens here is only this portion that's been stuck into the matrix, the inside, has been crystallized to date. So the first thing is the NADH loses its electrons, or donates electrons to an FMN. An FMN is a flavoprotein. It looks a lot like FADH2, but it's just the F part of FADH2. Okay. Then there's a whole series of these iron sulfur centers, and they just pass. So it's sort of like, you know, those old fire lines where they would pass the bucket of water along the line. That's sort of like what's happening here. Because instead of the buckets of water, they're passing electrons. It just jumps from iron sulfur centers to iron sulfur centers to this N2 protein of this complex. Okay, and N2 is also an iron sulfur protein. But what happens on the inside here is really only hypothetical right now because they haven't been able to crystallize it. It's really difficult to really understand on a molecular level what's occurring, but they believe that there's something similar to the Q cycle, which we'll talk about in the BC1 complex. But this is where, and this you know, panhandle part of the protein is where the protons somehow get transported from the N side to the P side. The N2 protein then donates the electrons, or gives electrons to the coenzyme Q that's already there waiting. So now Q becomes QH2. Then this QH2 can go on, and what complex will it be going on to directly? 3, right? You bypass complex 2. Right? So we have NADH, gives electrons to FMN. Then there's all these iron sulfur centers, which gives it to N2, and N2 passes it off to Q.
So two protons go in. Well, why are there 4 protons going out?
Because these 2 protons are going to the ubiquinone. There's 4 additional protons that go out. And so, and the mechanism by which, at least as of this day, the mechanism by with which the protons get shuttled are really unknown. And once again, I don't want you to get caught up on the number of protons, because once, you know, some would say, oh, well, is it really just a net of 2 molar equivalents of protons, or is there a net of 4? That's not important. It's more than 1, and the fact is that it's being shuttled across the membrane. Next, I'm going to do complex 2, even though this is where, if you start off with FADH2, where it comes into play. And if you notice here, it only has like really one helix that kind of sticks out into the end on the P side, but it's predominantly only on one side, the N side. And this is the only membrane-bound enzyme of the citric acid cycle, because remember, it's the succinate dehydrogenase. And so it's the one that, in the citric acid cycle, synthesized FADH2. What happens here is that FADH2 then gives its electrons to iron sulfur centers, which I can't see them, but hopefully those of you who are not color challenged will be able to see them. But there's a ubiquinone that's already there waiting. Similar to what happened, what we saw in complex 1, where there's already a ubiquinone. There's a ubiquinone there that's waiting, a Q, coenzyme Q, which becomes QH2, and then it can leave. And it just leaves. Okay, there are the important phosphatidylethynylamines to help anchor it in. But I want you to pay attention. This is one of my, I think it's really neat, but because there's a good sports analogy. But there is heme B, which is this heme right there, which we've seen hemes before. Where's the most obvious place that we've seen a heme? Hemoglobin, right? And what did the heme do? It had an iron in it. Hemes have to use iron. It carried oxygen, okay? And the way it did was was based off of the oxidation state of the iron, because you can go between the two different iron oxidation states. And so that heme is there. That heme actually does not have a direct role in the electron transport chain at all. Why do you suppose that heme is there, especially at that location? Close. This is like the catcher. What does a catcher do in the baseball? It catches the ball that gets by the batter, right? And so what happens here is things are working so fast. Those electrons are just pumping all over the place. Occasionally, you're going to have an errant electron get away. You don't want that electron to get away. And so that heme is there as the catcher's mitt. And so that heme, or a sponge, if you want to think of it that way, and that's my word. I'm sure your book won't call it a catcher's mitt or a sponge. But it's there to suck up or to grab the errant electron and then to toss it back to the waiting coenzyme Q. Okay, so it's just there to catch any electrons that were to get away. Because you don't want electrons to get away, because what happens if you just have those free radicals floating around? So those who had chemistry of cancer or neurochemistry talked about some of these. You can get cancer, but what do they attack? What can the free radical attack that's there in the mitochondria? Pardon? Well, just proteins in general. What else can it attack? The membrane, the lipids. I mean, it can just start to degrade everything, and that would ruin the efficacy of the mitochondria, and ultimately could lead to deleterious effects.
But the protons do not pass through there.
But there are no protons, because it doesn't fully go all the way to the P side. There are no protons that go through. The protons from the FADH2, oh, whoops, I hit the wrong one again. Sorry. The protons from the FADH2 are just regenerated back into the matrix side. Okay, so there's no net movement of protons.
This is the complex that you said directly links
The citric acid cycle.
to the ATC.
Because you can think of this portion of the complex is the part that's involved in the citric acid cycle, and it's stuck to the part that's in the membrane. Okay, and that's the reason why F8H2 doesn't give as many ATPs. You only get 1.5 molar equivalents versus 2.5. Because if you start with NADH2, you get protons moving across from complex 1, 3, and 4. If you start with F8H2, you only get the protons moving across on complexes 3 and 4. So you forego complex 1 altogether. This is complex 3. This is the one that I've worked on. There are lots of cardiomyopathies and diseases that are associated with it. I mean, it's huge. It's also called the BC1 complex. There's a lot going on. There are multiple hemes. There are two B hemes called heme BL for low potential, heme BH for high potential. There's the heme C1 and cytochrome C1, which is different than cytochrome C, which once again I apologize for the confusion that I know it will cause. And then we also have cytochrome B. There's a lot that goes on. This is a massive complex. But one of them is called the risky, R-I-E-S-K-E, the risky iron sulfur protein. And to me, since I took a lot of music, it reminded me of the hammer on a piano. What does a hammer on the piano do? Right, it hits the string, to make the sound. This one, it's really cool because it literally is what flicks the electrons from where the coenzyme Q, oh, this is frozen up again, where the coenzyme Q is coming in and takes it up to the heme C1 to give it to the cytochrome C. Okay. But we'll see. So it does. It just goes down, up and down, up and down, up and down. And that's the one that has to move like 150,000 times per second. And if you notice, this is like a dimer of a heteromers. And so technically there are two BC1 complexes that come together to form like a mega complex, like for the quaternary interactions. And so the risky protein of the one complex actually takes the electron from the other complex. So it's like a you scratch my back, I scratch your back kind of thing. This is where the Q cycle occurs, because ultimately you're going to be taking the electrons from coenzyme Q, 2 electrons, but you take them one at a time, so there's not a short circuit. Because the cytochrome C can only accept 1 electron at a time, or it accepts 1 electron there, I should say, at a time, and then, but you're getting 2 electrons, and so I'll show you how that happens. The figure, and there are antibiotics and also poisons, toxins that are targets to cytochrome BC1. Like there's antimycin and some of these that will target these, and because if it can eliminate the Q cycle or something like that, it'll short circuit it and can kill off, bacteria or even humans if it's a human toxin. This is the figure. I hate this figure, but this is the figure that your book shows. And I'll try to explain this figure, and then I'm going to try to draw it, except I can't draw it nearly as pretty. First off, they cut out the hammer, like the handle of the hammer. And so you have to just imagine that it's moving there. These are 2 separate BC1 complexes. Because what happens here, is that there are 2 half reactions that gives the overall net equation that they're trying to show, and they're trying to show that what happens is, let's say either from complex 1 or complex 2, you have this QH2, and it comes in by the low potential site. But it only gives 1 electron. It gives 1 electron off to the risky protein, which is going to then take it up and give it to cytochrome C1 to give it to cytochrome C. So that's 1 electron. Rather than just waiting, it gives the second electron down to the low potential B heme. And so now it's just a regular coenzyme Q, and so it actually leaves the top, leaves from that P side, and can go back. I know it looks weird, that makes it look like it's going to BC1, but it can now go back to complex 1 or complex 2. Well, this 1 electron goes through the B hemes down to a coenzyme Q that's already there waiting. Okay, so there's a regular coenzyme Q, and so it takes 1 electron and it gets pushed over to become a semiquinone. So this radical is not just out there floating around. It stays in the BC1 complex. So then what happens is when a second QH2 comes in from complex 1 or complex 3, which is what they're trying to show here, is it still gives 1 electron to the risky, which goes up to cytochrome C eventually, and it gives 1 electron down through the B hemes, but instead of having a Q there, it's got the semiquinone radical there. And so now this semiquinone radical, it accepts 1 of the electrons, and it's now a QH2, which can leave to go back up to another BC1 complex to give one electron. That's why it's a Q cycle, because at all times you actually have two forms of coenzyme Q on that BC1. One form is the coming in is QH2. The other one down on the inside is either going to be just coenzyme Q or a semiquinone, because it's going to accept one electron and the other electron goes on up to cytochrome C. Okay, so let me see if I can draw it and explain it as I draw it a little better, because it's really important, and this will be where we leave off for the day. So we have our we have our membrane, which I'm only going to draw this, but this is in the membrane, because that way I can draw everything else. So what happens is here we've got, that's going to be cytochrome C, because it's waiting for its one electron. So QH2 comes in, it gets inside cytochrome, the BC1 complex. It gives one electron up to the risky protein, and the risky protein gives it to the cytochrome C1, and which ultimately gives it cytochrome C, so that way cytochrome C can leave. But then it would still have one electron left. So what it does is the second electron then goes down through the B hemes. I'm just going to write B because I'm going to run out of room. And so the BL to the BH, oh, I didn't mean to cut it, to BH, to a Q that's already there, that's waiting. Well, whenever that Q takes that electron, that one electron, it now becomes a free radical. It becomes semiquinone. So this QH2, the original QH2, is now just a regular Q, and it can leave. It can either go to another BC1 complex to wait down on the bottom, the inside, or it can go to complex 2 or complex 1 in order to be reduced. So now we have this semiquinone that's down here. So what's going to happen is that we get, let me clear this. So once again, we still have our membrane, but now we've got a semiquinone that's down there waiting. So the next QH2 comes in, it gives one electron up through the risky protein to cytochrome C, so cytochrome C becomes reduced and it goes on to complex 4. The second electron goes down through the B hemes to the semiquinone, and so now that semiquinone becomes QH2. So it can go to another BC1 complex to do the same Q cycle. So that's why at all times, if you're healthy, you're going to have two forms of Q in the BC1 complex. One is on the P side and one is going to be on the N side. The one on the P side is always going to be the QH2 giving off electrons. The one on the N side is going to be either semiquinone accepting an electron to become QH2 or just coenzyme Q becoming a semiquinone. So that's why it's called a Q cycle. You may want to sit there and kind of mull that over, because it is very important, because like I said, there are a lot of antibiotics and drugs and problems with the Q cycle that causes different types of mitochondrial cardiomyopathies and mitochondrial-based diseases.
Sorry, can you just repeat the second Q2? Where does it go?
Oh, it will go on to like another BC1 complex to do the same Q cycle. Because it can now it's got two whole electrons that can go and donate the first one, right? And so that's why it will leave and it will go to another respirosome, in theory, to go on and do it. So you have one net coenzyme Q being fully reduced, but in reality it's two of them working half and half in order to do that. Okay, because otherwise it would short circuit. You get a buildup of electrons or something, since cytochrome C is only taking one at a time, and you would die. And so, all right, I'll go ahead and